Imagine trying to build a 33.9-kilometer seawall across the Yellow Sea, where the seabed is soft mud, tides rise and fall by about 6 meters twice every day, and currents can move 10-ton rocks like pebbles. That was the challenge South Korea accepted with the Saemangeum project. In 1991, the government announced an enormous plan: connect 4 dike sections between islands and headlands, block 2 river estuaries, and turn about 401 square kilometers of sea into reclaimed land. The vision was huge: a new development zone, industrial areas, infrastructure, and space for hundreds of thousands of future residents. But before any city could exist, engineers had to defeat the seabed. The southwest Korean coast has deep tidal sediment deposited by the Mengyung and Dongjin rivers. At low tide, it looks like an endless mud plain. At high tide, that ground disappears beneath 6 meters of water. Building directly on it would be asking for trouble. Heavy embankments could cause the saturated sediment to deform, tilt, and fail. So construction started from below. Floating cutter suction dredgers were brought offshore. Their cutter heads broke apart the unstable sediment, while powerful pumps sucked the material into slurry and sent it through floating steel pipelines to disposal areas. These machines worked continuously, removing millions of cubic meters of material. The goal was to reach stronger clay beneath the unstable mud. In some locations, crews had to remove around 20 meters of sediment before reaching competent ground. And even that excavation had a deadline. Every tidal cycle could refill the trench with fresh sediment. Miss the working window, and the sea basically hit the reset button. During short periods of slack water, barges carrying thousands of tons of crushed rock moved into position and dumped their loads onto the seabed. Only the beginning. The seawall was still waiting to rise. The foundation was only the first battle. Now came the part that would make this project look completely insane: building an enormous embankment in the middle of the sea. This was not a conventional concrete wall. Saemangeum was essentially a massive artificial mountain built across the seabed. Its base reached roughly 535 meters at the widest points, with an average width of about 290 meters. The structure rose around 36 meters on average, reaching as high as 54 meters in places. Yet only about 11 meters would remain visible above the water. The rest was hidden beneath the surface. So how do you build something that huge without watching it slide into the Yellow Sea? Engineers first created a massive sand core. Dredged marine sand was pumped through floating pipelines and deposited layer by layer. But loose sand underwater has a serious problem. It wants to spread everywhere. The solution was surprisingly clever: giant geotextile tubes. These enormous fabric cylinders, some 30 to 50 meters long, were filled with sand slurry until they expanded into thick structural barriers. Around 26 kilometers of these tubes were used throughout the project. They acted like temporary retaining walls, keeping the sand core contained while the material drained and gradually consolidated. Timing was critical. A tube had to be filled, positioned, and secured before the next tide arrived. Otherwise, the rising water could collapse the fabric and send the freshly placed sand sliding back into the sea. And then came the armor. The seaward side was covered with layers of rock riprap. Instead of forming a vertical barrier, the rocks created a broad sloping surface that absorbed wave energy. Water could travel between the gaps and retreat without simply smashing straight into a wall, but one missing stone could become a much bigger problem. If waves removed a rock, the empty space could undermine the stones above it, creating a chain reaction along the slope. Meanwhile, the inner side received compacted fill and a clay cap to protect the sand core from water infiltration. Eventually, a highway would run across the finished structure. As the 4 seawall sections extended toward each other, the openings between them became smaller. But the amount of water moving in and out of the 401 square kilometer enclosed area did not magically disappear. The same enormous tidal volume now had fewer routes to escape. That meant one thing: the remaining currents became brutally powerful. During spring tides, flow through the final openings could exceed 6 meters per second, around 21 kilometers per hour. At that speed, loose rocks were practically useless. A boulder could hit the water, roll across the seabed, and vanish downstream before anyone could celebrate. Even wire cages filled with rocks, known as gabions, could be torn apart by the current. So engineers had to change the strategy. Instead of simply pushing material horizontally into the opening and trying to make the wall narrower, they began raising the seabed itself. The idea was simple but extremely difficult. Make the gap shallower, not necessarily smaller. With less water depth, the current would lose enough energy for the construction material to finally stay in place. The northern gap became the first major test. On June 10, 2003, construction crews launched the closure operation. During the brief period of slack water, when the current almost stopped, trucks dumped enormous quantities of rock and gravel into the opening. But the real breakthrough came from the gabion bags. These were massive wire mesh containers packed with rocks. Unlike individual stones, the mesh kept the material together. When the current attacked, the bags could deform and settle instead of simply rolling away. The process was painfully slow. Dump material. Wait for the tide. Measure the seabed. Let the current reverse. Dump again. Every cycle raised the underwater sill only a little. Centimeter by centimeter, the seabed rose. Eventually, the northern gap became shallow enough for the construction material to survive the current. And that created a new problem. The water that had previously escaped through 3 openings now had only 2. The pressure on those remaining gaps increased dramatically. The final closure would require both southern openings to be attacked simultaneously. 2 gaps, each about 2.7 kilometers wide. 1 operation, 1 chance. Because if one closed before the other, the entire tidal flow would be forced through a single opening, and construction there could become physically impossible. So both fronts moved together. As the tide slowed, convoys of dump trucks rolled along the seawall. Bulldozers waited at the edges, cranes positioned themselves on barges, and survey boats constantly measured the current. Then came the signal. Hundreds of trucks began dumping simultaneously. Rock poured into the brown water. Gabion bags followed. Cranes lowered massive concrete blocks while bulldozers pushed material toward the openings. The sea fought back. Rocks rolled away. Water tore through the gaps. But the gabion bags stayed together, settling and locking against one another. Every tidal cycle brought another load. Eventually, the underwater sills became high enough that the current could no longer move the construction material. The impossible had happened. The 2 gaps were closed, but a closed seawall was not automatically a safe seawall. South Korea's western coast regularly faces typhoons, and storm surges can raise water levels rapidly. The exposed sand core still needed protection. Crews covered the outer slopes with enormous quantities of riprap, carefully creating the correct slope so waves could lose energy instead of climbing over the structure and attacking the interface. 2 major sluice gate systems were also installed to control water exchange between the enclosed area and the sea. These gates became critical for managing water levels inside the reclaimed zone. Then, on April 27, 2010, the project officially opened, 19 years after construction began. The finished seawall stretched 33.9 kilometers, making it longer than the Dutch Afsluitdijk record it surpassed. The wider Saemangeum development was planned to transform the enclosed area into industrial zones, infrastructure, and a new city intended to accommodate hundreds of thousands of people. And the transformation was remarkable. Pumps removed trapped seawater. Dredgers moved sand into the drained areas. Places where tides once moved freely were becoming solid ground. But this enormous construction achievement came with a serious environmental price. The Saemangeum tidal flats had supported hundreds of thousands of migratory shorebirds and provided feeding habitat along the East Asian Australasian flyway. Once the tidal system was blocked, much of that ecosystem changed dramatically. Fishing communities were affected too. Thousands of people who depended on shellfish, fish, and seaweed farming lost access to the estuary that had supported livelihoods for generations. That is what makes Saemangeum more complicated than simply a story about a giant wall. It is a story of engineering defeating one of nature's most powerful forces, and of what humanity gives up when it does. Today, the wall still stands. 33.9 kilometers of rock, sand, concrete, and engineering separating land from the Yellow Sea. The city may rise behind it, but every wave hitting that enormous structure is a reminder of one simple fact. You can build a wall against the sea, but you can never truly control the sea.